Hello everyone, I am Abhijit Das, a PhD scholar with the Department of Computer Science and Engineering at IIT Guwahati. I work in the broad area of advanced computer architecture under the supervision of Dr. John Jose. Research in computer architecture often, if not always, involves hardware, and designing actual hardwares in an academic research is not always feasible, mainly because of the cost. Hence, computer architects make use of industry standard simulators to realize their design and assess the performance. Today, I am going to talk about one such simulator called GEM5. GEM5 simulator will be used for all the simulation based assignments in our NPTEL course Multi-Core Computer Architectures, Storage and Interconnects. This is the outline of my discussion. I will start with a brief introduction about GEM5 and the key features it has. Then I will show how to build and run a simulation on GEM5 while telling the simulation flow. Then I will talk about how to make sense of the data that we give as input and the values that we get as output. Finally, I will conclude the discussion by giving a brief tour of the GEM5 directory. What is GEM5? There was a popular simulator called M5 by the University of Michigan in 2006. Around the same time, another simulator called GEMS by University of Wisconsin-Madison existed. GEMS was equally or even more popular than M5. However, both of these simulators had some flaws, and hence the developers thought that they could combine. Then came GEM5, which combined the goodness of both these simulators. GEM5 uses the CPU models, instruction set architectures, I/O devices and other infrastructures from M5 simulator and the Ruby memory module, including cache coherence protocols and interconnect models from GEMS simulator. And in no time, GEM5 became one of the most popular computer architecture simulator. The popularity of GEM5 can be gauged from the fact that it has around 2500 citations. This is the definition that I have taken from the official website, which says the GEM5 simulator is a modular platform for computer system architecture research, encompassing system level architecture as well as processor microarchitecture, meaning GEM5 can model and simulate everything, right from the system calls, operating system kernels, processors, memory, interconnection and everything else that we can think of in a computer system. Coming to the key features, GEM5 runs in two execution mode: system call emulation, where only the processor and memory is emulated, and full system, which is equivalent to running a virtual machine on a system. GEM5 has these binaries for the simulation: gem5.debug, gem5.opt, gem5.prof and others. GEM5 also supports different instruction set architectures like Alpha, ARM, MIPS, Power, RISC-V, Spark, x86 and other. As we know that x86 is one of the most popular instruction set architecture used in personal computing systems, and ARM is another popular instruction set architecture used in mobile computing systems. GEM5 also supports different CPU models like atomic simple CPU, timing simple CPU, in order CPU and out of order CPU. GEM5 uses two memory models, Classic taken from the M5 simulator and Ruby taken from the GEMS simulator. It also supports two different interconnection networks, Simple and Garnet. For our simulation based assignments in the course, we will use system call emulation mode in gem5.opt binary with alpha instruction set architecture. We will simulate atomic simple CPU with Ruby memory model and Garnet interconnection network. GEM 5 can be built and run on different operating system platforms like Linux, BSD, macOS and Solaris, and having a 64-bit machine is an advantage. However, GEM 5 comes with certain dependencies like a repository where it is kept and maintained, which could be either a Git or Mercurial. GEM 5 is also dependent on GCC or G++ compiler, Python, Ascons, Swig, M4 and Z library. In a general Ubuntu system, we can run the following command and install all the GEM 5 dependencies. I have already installed them, so I am not showing here. After installing the dependencies, we can use this command to get a working copy of GEM 5 which I have kept on a GitLab repository. This customized version of GEM 5 will be used for all our simulation based assignments in the course. After getting the copy, we can build the GEM 5 simulator by using a command like this, where ascons is the make, build is the directory, ISA can be one of the following and binary again can be one of the following. As I mentioned before, for our simulation based assignments, we will use alpha ISA and gem5.opt binary. Then the command is followed by -j, which specifies the number of jobs to be performed, and typically it is one more than the number of CPUs that we have in our system. Please note that this number of CPUs has no connection with the simulation, but they just make the build faster. So we can use this command and get started. Let me show you. I will go to the terminal and reach the GEM 5 directory. I am inside the GEM 5 directory now, and if some of you are not sure about the number of CPUs that you have in your system, you can type something like ls CPU and it will show you the number of CPUs that you have. In my system, I have 8 CPUs. Now I can start the building by using the command ascons build the directory. I am building alpha, then gem5 opt, -j is for specifying the number of jobs, and since I have 8 CPUs, I will give it as 9, and the simulation will start. Typically on a 4-core system, the simulation takes around 20 to 25 minutes to build, but since I have built it before, it need not take that long in my system, and hence we are done with the simulation. This message telling done building targets assures you that your build is successful. Now going back, we can run a command like this to get the help available with gem5 binaries. For example, we can use this command to see what are the available help options with gem5.opt binary. Let me show you. gem5.opt, and then I can type --help to see the available help options. As we can see that there are different options to debug and get the stats with this gem5 binary. Going back to the slides, after this I can run the gem5 build with the configuration script. And again I can type something like --help to see the available options with respect to this configuration script. Let me show you. So I have to go to the build directory where the alpha ISA is kept with the gem5 opt binary, and I have to specify a configuration script which the gem5 uses for the simulation. So the script that I am going to use is kept in a directory called configs example se.py. This se is for syscall emulation, since we are using syscall emulation mode for our assignments. And again we can type something like --help to see a long list of help options. From the available options, let me use -c, which says that on the command line you can specify the binary to run in syscall emulation mode. Let me go back to the slides. After this, we can run this command to have a sample simulation run on GEM 5. Let me show you. The configuration script, which is kept in configs example se.py, then I am using the -c help option, and then I am specifying a test program which is kept in a directory called test. Inside test programs, there is a hello world program. I am sure most of us, when we learn a new simulator, the very first program that we run is a hello world. So I am going to run a hello world program on GEM 5 simulator. Here I have specified the binary of the hello world program, and when I press enter, it prints the hello world message. This is a proof that my build and run is successful on GEM 5. After the hello world message, you can see a message called exiting at tick this, because the target called exit, because after the hello world message the simulation had nothing else to do. Going back to the slides, this is the same command that I have used for sample run. We can also try simulating full system mode, but since it is out of the scope of our syllabus, I am not showing here. To understand the simulation flow, what we do is we give an example Python script. In this case, we gave se.py, which instantiates simulation objects and sets their parameters. This is then interpreted by a library of simulation objects which are already kept in GEM 5. Then with this interpreter, the corresponding C++ simulation objects are assembled and configured according to the given Python script, and from there the actual simulation begins. To understand it better, this is the flow of simulation from different functions. As we can see here, the GEM 5 simulation begins from a file called main.cc, and then it goes to another file called initiate.cc, and this way it passes through different configuration scripts, like here in this case se.py, and then finally it calls the actual C++ constructors and the simulation begins. Everything in GEM 5 is simulated around something called sim object or simulation object. All the physical entities like processor, memory, interrupts, instruction set, architecture, everything is a sim object on GEM 5. For example, here for alpha ISA, interrupts is a sim object. For alpha ISA, ISA is a sim object. And this is a long list. I have just taken a snapshot of the available sim objects on GEM 5. After completing the simulation, we have to make sense of the data that we have given as input and the values that we have got with respect to the input. So for this, let me go to the GEM 5 directory. I am inside GEM 5 directory now, and here I have a directory called m5 out. The very first file in m5 out directory is config.ini. If I open this file, I can see that there are different simulation objects configured with different values that I have used during my simulation. So here root is one such object, and system is another object, clock domain is another object, CPU is another object, and so on. This is the file where we come back after simulation to cross check and verify whether all the configuration parameters that we have specified during the simulation are correct. Here, for example, the type of CPU that I am using is Atomic Simple. So, if I see this message, I am assured that this is the correct configuration that I wanted. Going back, there is another file called config.json, which is the same configuration file but in JSON format, and I am not showing here. Next is a file called stat.txt, which stores all the output results. This is the file that is visited the most after every simulation. After the simulation is complete, we come back to this file to get all output values with respect to the configuration scripts that we have provided. For example, here you can see different parameters with their respective values, like for how many simulation seconds the simulation has run, for how many ticks the simulation has run, what is the final tick, what was the simulation frequency, and so on. So, we will frequently visit this stats.txt file once we start our assignments. Going back to the slides, this is what I have already explained. Now, in the final part of my discussion, I will give you a brief tour of the Gem5 directory. So, let me take you there. I am inside Gem5 directory now, and the very first directory that I see is called binaries. It contains the spec CPU 2006 benchmarks that we are going to use for our assignments. We will come back to this once the assignment starts. Next directory is called build, which contains the instruction set architectures that we have built for our simulation. In this case, we have built alpha instruction set architecture, hence we see a directory named alpha here. Next directory is called build options, which contains all the available options for simulating different instruction set architectures. For example, in our case, we have built alpha instruction set architecture. Similarly, we can build this or any other ISA that is available. Next directory is called configs, and it contains all the configuration scripts. For example, we used a configuration script called se.py, and it was inside config and then example and se.py. This is the script that I have used for my sample run of Hello World program. In this point, I want to tell you that all the configuration scripts in Gem5 are written in Python, whereas all the simulation objects and other source codes are written in C++. So, we can say that the front end of Gem5 is configured in Python, whereas the back end of Gem5 is coded in C++. Next is the ext or the external directory, which includes external frameworks like DRAMSim2. It is an independent simulator, but here it is integrated with Gem5. Similarly, Descent, MacPet and others. Next is the M5out directory, which I have already explained. So, going back, next is the source directory, which contains all the source code and simulation objects, meaning here all the codes are mostly written in C++. This is the backend of Gem5 simulator. Next is the system directory, which contains some system specific files for alpha and ARM instruction set architectures. Next is the test directory, which contains different test programs to check the simulation. For example, we used a program called Hello, and this was taken from here. Going back, the last directory is called util or utility, which contains different utility files and function to check the working of Gem5. Going back to the slides, these are all the things that I have already explained. These are the references that you can follow for understanding Gem5 better. I request all the learners to complete the simulation process in their respective system and get themselves familiarized with the GEM5 directory. We will give more detailed instructions with respect to specific assignments in due course of time. If you have any questions related to the building and running of GEM5, you can get back to us on the discussion forum in the course portal. Thank you.